Thanks everyone for joining another Protocol Symposium. Today, I'm very happy that we have István. He's a researcher at Eötvös Loránd University. Yay, I pronounced it. Uh, and he's going to talk about manipulating RANDAO on Ethereum. Thanks for accepting the invitation, István, and take it away, please.
Thanks a lot for the invitation and the possibility. This is really a special moment also for me and also for this paper, because this is a world premiere. So this is a work in progress. It's not published yet. We didn't publish, not even as a preprint on arXiv, but soon, hopefully, it's going to be out. So you are the first ones to hear about this work publicly. So yeah, and I think it's really valuable what you guys are doing with this Protocol Symposium. Like I watch many of your videos, and I think it's really helpful for the community to catch up with all the latest research in the field. So this is a joint work with Abel, Peter, János, and Bence. Okay, so what are we going to cover in the next 40-45 minutes? Really important. Feel free to interrupt me anytime. If something is not clear, yeah, feel free to just ask a question, unmute yourself. Yeah, we are all here to learn. So first, I just want to make sure that we are on the same page. I will give some preliminaries on how Ethereum selects validators and how the RANDAO works, which is a distributed randomness protocol, how we can manipulate it. Then I will describe two main strategies. Selfish mixing, that you might know from the great blog post of Tony Verstetter on ETH Research. And we also define a new class of strategies, namely that an adversary can fork the blockchain in order to increase the manipulative power. I'm not going to talk about this agenda point because it's really technical, and that's where all the detail is. And I don't want to bore you guys with all these gory details. And then in the second part of the paper and also the talk, I want to talk about our experimental analysis, where we look at the beacon chain and Ethereum, whether all these manipulations that we define happen in practice or not. I will mention also follow-up work from two researchers, Gottfried and Arantxa from Ethereum Foundation. That's also going to be an ETH Research post soon. And then I would be really happy to open up the floor, and feel free. Like, we had a little discussion before the talk with Mohammed, and yeah, I think there are many interesting questions that we as a community need to have consensus on. So yeah, there will be some questions, and maybe it's worthwhile also for the community to hear different opinions. I have my own, I will share it, but also feel free to come forward and share yours. Okay, so maybe some of you need to leave earlier. So here's the TLDR. Okay, so these are the numbers. There's a very recent work published at AFT24 a few days ago. It was in Wien, Austria. And they define the selfish mixing attack and create a Markov decision process, solve it, and they find that the adversary can slightly have. So if you have, let's say, 25% of the stake, then you can increase the number of blocks that you win in the long term to 25.02%. And we realize in this work that you can not only do selfish mixing, but you can also do selfish mixing and forking. And this gives a slight advantage to the adversary if the adversary or a coalition of the adversary, if it has more stake than, let's say, 15 or 20%. Okay. So, and yeah, this was the question of Mohammed, like, is it bad? Is it not bad? I will leave this discussion to the end of the talk. And another spoiler is, so what the adversary needs to do if it wants to maximize its power, manipulative power over the RANDAO. And what we can see here is that forking is relevant only for major staking entities, but as the stake grows, also the probability that you need to do forking also increases dramatically. So as the more powerful you are, selfish mixing gets, it's okay if you don't know what selfish mixing and forking, I will describe these in detail. And for instance, just as a reference, like Lido has 30% of the stake. So if Lido would want to act optimally according to selfish mixing and forking, then 40% of the time Lido would do some nasty things against the consensus protocol and would only incentivize to act honestly 60% of the time. So just as a reference, ideally what we would like to see is that this whole figure is fully blue. So but the point is that the RANDAO does not give cryptographic guarantees for us for unbiasability. So ideally, all these colors of yellow, red, and green would never happen. But sadly, the RANDAO is not an unbiasable distributed randomness beacon. And I don't want to give some spoilers here. You need to bear with me and stick till the end, where you will see whether all these manipulations happen, if at all, or to what extent. Okay, so let me start from a little bit from Adam and Eve. So why do we need randomness for consensus? Because there's a super famous theorem, the FLP theorem, and the authors got it's a super famous impossibility result for the theory of consensus, and the authors got Turing Award for this paper. And the bad news is that deterministic asynchronous consensus is impossible. But the good news is that with randomization, we can have consensus in constant expected rounds. So that's good, but this result only holds for the permissioned consensus, and notably Bitcoin and Ethereum and other cryptocurrencies work in the permissionless consensus setting. If you don't believe me, it's fine, but you can read a nice proof in this great blog post. So, and the similar result was recently proven by Louis Pye and Ralph Garden, which says that even in synchrony, without randomness consensus, it's impossible. So the bottom line is that if we want consensus, and in cryptocurrency we do need it, we need randomness. So Ethereum specifically also needs randomness to select the leaders in each round. Okay, so why I started, this is just a funny story, why I started working on this problem is because last year, one of my favorite conferences started to choose the submission period, the submission date, given the Ethereum's RANDAO reveal. So this is a great conference. So I guess there are many researchers here in the audience. So if you have a good research paper, you should submit to this great venue. And they select the submission deadline according to RANDAO reveal, according to the output of this distributed randomness beacon applied by the Ethereum protocol. And I was thinking back then, a year ago, when I wanted to submit that paper, would it be nice if we could bias somehow this beacon? And then I started looking to it, and the answer is yes, we can bias this beacon. And so, okay, there are many dragons here. I will cover the details. So how does leader selection in Ethereum works? I assume many of you know, but still just to refresh your memory and to be on the same page. In Ethereum, time is divided into epochs. Each epoch contains 32 slots, and each slot lasts 12 seconds. And each validator has 4 seconds to publish their block. And what do we do is, after each epoch, somehow magically, that's the RANDAO, I'm going to describe it next, outputs at the end of the epoch, we output a public seed S, and this seed S is used in a pseudorandom permutation in a PRP, which determines the validators in not the next epoch, but the next but one epoch. So sometimes I will be just lazy, and whenever I say next epoch, you should think not the next epoch, but next but one. So the RANDAO outputs a seed here, which determines the list of validators who are entitled to propose a block in epoch E+2. Okay, let's zoom in now into a single epoch. And each slot, each validator needs to publish a contribution to this RANDAO. So validator I will publish a randomness contribution Ri. What is this Ri? Ri is just that the validator signs with its secret key the epoch number. This signature is a BLS signature, so it's a deterministic signature. So the randomness, this randomness contribution cannot be molded. There's only one valid randomness contribution by the validator, and moreover, this is publicly verifiable because it's a signature. And at the end of the epoch, what we do is, it's a little bit oversimplification, but it's good for our purposes. What we do is just we XOR all together these random values, and this is going to be our seed. And we feed this seed into the PRP, and given the list of validators, the validator indices, that's going to be the input to this PRP. So we shuffle, we permute with the suitor and the permutation and the seed, the list of validators, and we take the first 32 validators, and those guys are going to be the validators in the next but one epoch. In Ethereum, the protocol gives this time for the validators to be able to realize that they are going to be the leaders, and to give them time to act accordingly. Okay, so if you go to Etherscan or to your favorite blockchain explorer, you can see this RANDAO reveal. So this is how, in practice, this randomness contribution look like. And this is how it looks like. And yeah, one important point is that if you don't include this RANDAO reveal Ri, or it's invalid, then the whole block is invalid. So it's an integral and substantial part of the block. Without it, the block is invalid completely. So essentially, you just have two choices, either to publish or not publish your block. Okay, feel free to interrupt me anytime. So the first strategy, which was widely known in the community, is called selfish mixing. So imagine that the adversary, this little devil, your favorite validator, has, let's say, two tail slots, the 30th, the penultimate, and the ultimate slot in the epoch. Then the adversary has four choices, either to publish both of the blocks. Then this seed S is going to be the XOR of R. Let's just R denote all the randomness before in the epoch. So then the seed will be R XOR R30 and R31. The adversary can decide to miss the last block. Then the seed will be R XORed with R30. Or the third option could be that the adversary decides to publish the last block, but not the penultimate. Then the seed will be R XOR R31. And the last option of the adversary is that it can just miss both of these blocks. So essentially, if the adversary has many tail slots, then it can look into the future and see what this seed will be. And why is it good? Because then the adversary can choose which seed will be beneficial for it. So it might be even incentivized to miss both of the blocks in case if the next but one epoch will give it a lot of blocks. So this is just a toy example. Let's say the adversary looks into the future, and okay, if I publish both, then I don't sacrifice any of the slots in this epoch, but I will gain 5 more slots in epoch E+2. And there are 3 more possibilities, and this is just a toy example. And in this example, let's say this one is the best strategy, that the adversary is going to miss the last one, but publish the penultimate, even if this incurs a sacrificed block in epoch E. but it will give eight blocks in the next but one epoch. So this is the idea of selfish mixing. And more generally, and this is the concrete example. For instance, Lido had in this slot 1049, 812, or in this epoch, sorry, Lido had 8 tail slots. So 8 tail slots essentially corresponds to 2 to the 8 possibilities. Like at each slot, Lido could decide, should I publish this block or not? Should I withhold this block or not? And so on. So this gives Lido 2 to the 8 possibilities. We can encode this 256 possibilities as an integer from 0 to 255. And the y-axis is the number of slots that Lido would have gained if Lido would have chosen that strategy. But in reality, we need to account it. We need to account the strategy for the sacrifice blocks. So you see that there are some strategies that would give net negative slots for Lido. But in this example, Lido decided to publish all the blocks in these tail slots. But still, what we can see is that Lido could have done better. Namely, Lido gained 10 slots in the epoch E+2, but if Lido would have acted strategically, then it could have had 13 slots. Okay, so what could be the objectives of a RANDAO manipulation? I mean, the most natural is that you just want to maximize the expected number of slots in the long run. This is the most natural objective. The second one is also interesting, namely that you have a target slot in mind. Let's say you know that there's an airdrop or NFT launch or some liquidity or some pool is going to be introduced on Uniswap or something like that on an AMM. So you know a priori that, let's say, slot number 17 is going to contain a lot of MEV. Then you might be incentivized to get that specific slot. Yeah, so we call this the target slot utility or objective function. Or you could just focus on maximizing the number of slots in the next epoch, or any other ideas. In the paper, we just only focus on the first two objectives. The most natural one and this target slot utility. Okay, any questions so far? This was kind of well known in the community so far, and now I will continue introducing the new strategy if there is no question.
One quick question. Maybe it's too early for this question, but I'm wondering if we have ever detected suspicious activity of that resembles selfish mixing.
Okay, I will talk about it more in the second part of the talk. Yes, but good question. So yeah, we have experimental data and we looked at it a lot of, we put a lot of effort into looking into it. Okay, so yeah, I will come back to this later. Any other question? Okay, so let's focus on forking then. So imagine that slot n+1 and n+3 belongs to the adversary. So the adversary is supposed to propose a block in these slots. But in between the adversary, there's this honest guy at slot n+2. And this is called the ex ante reorg technique that was described in a paper by 3 attacks against proof of stake Ethereum. It was published in 2022 at FC, Financial Cryptography. Maybe we can include all these references in the show notes. So the authors are Nusret Tash, Joachim Noy, David Che, and Barnabe Monno, and some other guys from the Ethereum Foundation. So the idea is that the adversary can decide ex ante. So before seeing this block, the adversary can decide to fork out this poor guy. How can the adversary do that? At slot n+1, the adversary does not publish a block, privately builds it locally. And in this slot, so these are the attestations, these are the votes. And for this attack, in this specific case, the adversary needs at least 20% of the stake. I will convince you why this is the case. Bear with me for a minute. So in this slot, the adversary will vote at this secret block as the head of the blockchain, but the honest guys don't see this block because it's not published yet. So the honest guys will think that the head of the blockchain is this published block. We advance to the second slot, slot n+2. The honest guys publish their block, but since they don't see this secretly built block at slot n+1, the hash pointer in the block header will point to the block n coming from slot n. So the adversaries, the honest guys will vote for this block as the head of the blockchain. The adversary is still going to vote for this block as the head of the blockchain. And finally, so the adversary is going to publish a block. And in fact, it's going to publish both of these blocks from slot n+1 and n+3. And it will also get the so-called proposer boost. Proposer boost is a Ethereum proof of stake specific vote that is only assigned to a block in that slot. So when the voting starts at the second part of this slot, the honest guys will think that this is the honest guys will deem this branch of the tree as the canonical if and only if 2 alpha plus the proposer boost is larger than 1 minus alpha. So the protocol says that if there's a fork, then you need to choose the branch of the tree that has more votes than the other one. So how many votes do we have on the adversary's side? We have 2 alpha. Alpha is the stake of the adversary. We have 2 alpha votes here, and we have the proposer boost here. And we have, on the right-hand side, we have 1 minus alpha votes here. Proposer boost at the time of this recording is set to 40%. So if you do the simple calculation, if alpha is larger than 20, then the adversary can fork out this honest block. So this is the idea of ex ante reorgs. Okay, now you can ask, if there's no question, now you can ask, why is this useful to manipulate the RANDAO? Imagine this following scenario. So the superscript corresponds to the epoch number and the subscript corresponds to the slot number. So if we see such a string, like the adversary controls the ultimate slot in the epoch, and the honest guys control the ultimate, the last slot in the epoch, and the adversary controls the penultimate and the first in the next epoch, then the adversary can just kick out, the adversary can fork out the honest block if its stake is larger than 20%. So the adversary, and note this wouldn't happen with selfish mixing. So selfish mixing, if there's such a string, then selfish mixing says, oh shoot, I cannot manipulate the RANDAO because the last slot doesn't belong to me. But the forking attacker can look out this guy and can decide, okay, I want to fork out the honest guy's RANDAO contribution. So don't like the RANDAO contribution of the honest person, fork it out. And the similar string, for instance, is that if the adversary controls the last slot in the epoch and the penultimate belongs to an honest guy and the 29th belongs to the adversary. And more generally, so there are many such strings where the adversary can fork out the honest guys. So for instance, if there are multiple adversarial slots preceding the honest guys slot, then last stake is enough for forking. For instance, if you have 2, then 50% is already enough for forking out this honest guys block. And there are many more such strings, so we can generalize it, but it gets a little bit uglier. But this is the general idea how we could launch an ex ante reorg to fork out the honest guys. So here's the decision tree. Let's say this is the, go ahead.
One quick question. In the previous slide, so my understanding is in one epoch we break we break attestators into like 32 parts or something, or like uh, it's not like the case that every attestator votes on every slot. So
True.
I think we are making some simplifying assumptions when we think of this red validator as like alpha in total, while maybe some part of this is only participating. So is it explicitly a simplifying assumption, or for some
Yeah.
reason it's
So I will have a slide on the system model, but let's just assume that in each slot, the alpha percent of the attestations belong to the adversary, and 1 minus alpha belongs to the honest guys. Yes, this is a simplifying, stylizing assumption. Yeah, it's true, but let's
got it.
let's simplify our lives, and we can give some also analytic arguments why this assumption is not far from reality, because the number of attestations is binomially distributed, but this is a huge binomial distribution. So the average, it's like a bell-shaped curve, which is really close to the average. So I'm happy to stylize it and say that in every slot, alpha percent will belong to the adversary, even if it's in practice is just a binomial distribution with alpha average and and some other
got it.
yeah.
Got it. Thank you.
So I just want to convince you on an example why this is useful for the adversary. So let's stick to this example where the last slot is the adversary and the penultimate is the honest guy, and the 29th is also belongs to the adversary. So at the end of the attack, the adversary needs to decide, because this is an ex ante reorg. So you need to decide whether you want to fork before seeing the honest block. I'm going to assume, okay, after this slide I will have so soon I'm going to describe all the system model and all my assumptions. But one really natural assumption is that the honest guys always propose in their allotted slot. So the adversary needs to decide first time to fork or not fork. If the adversary decides not to fork, then it's basically just a single. It's basically just selfish mixing. The honest guys will publish blocks 30, building on block 29. And in the last slot, the adversary can basically just have two choices, publish or not publish the block. But if the adversary decides to fork, then why would the adversary be incentivized to fork? Because so here note that the only scenario that the adversary can compute the state of the RANDAO output is scenario C, because scenario C, we don't have the contribution of the honest guys. This is not the best figure. I should have updated it, but this block builds on the adversary's block. So if we fork out this honest block, then the RANDAO output contains this R XORed with this contribution and this contribution, so without the honest guys. So if scenario C would give a lot of slots to the adversary, then the adversary would say, hey, I just want to fork out the honest guys because this would give me like a super high number of adversarial slots. But the adversary can change its mind after seeing after seeing the honest guy's contribution after slot 30, the adversary can decide whether I want to continue the fork, then I will publish this block and build upon this block 29 and publish the fork. Or the adversary could say, oh, this is not a bad RANDAO contribution. So what I would do is just publish this block on top of the honest guy's block, and I will just throw this secret block away. Or the adversary could even say that, hey, okay, let's just throw out all these 2 blocks because I like the RANDAO contribution of the honest guy. So the adversary can only compute scenario C a priori, but if C gives a lot, then it might be incentivized to fork. And more generally, the adversary can fork such a string. So if we have, this is maybe not the best notation, but if we have A1 adversarial slots, and after that H honest slots, then the adversary can fork. If it's a simple lemma, the adversary can fork out these guys if alpha is larger than this quantity. Okay, what about, so in Ethereum we can do, this was ex ante reorg, so the adversary needed to decide to whether fork or not before seeing the honest guy's block. What about ex post reorgs? Ex post reorg meaning that forking a block after the adversary sees it, which is a much powerful tool. But luckily for the Ethereum protocol, there's no known technique for ex post reorgs for non-majority stakers. But it can happen in practice. How? If a block receives a few attestations or votes, then how could this happen? For instance, if a validator publishes a block after 4 seconds, remember, you need to publish your block if you're a validator in at the first 4 seconds of the slot. If you don't do so, then it's really likely that most of the other validators will not vote on your block, and then you will get very low number of votes. In particular, if this number of votes is less than the proposer boost, then basically anybody can fork out you. So this behavior cannot force by the adversary. That's why we don't consider it in our theoretical model, but this can happen in practice, and we look at it in the second part of the talk. Okay, so system model, what are my assumptions? We assume idealized cryptography as usual, very natural assumption. Each block has the same value, so MEV is uniform. Each block, so yeah, this is a good question for follow-up work. Like, does the manipulative power of the adversary increases if we also consider MEV? But I will just assume for the sake of simplicity that MEV is uniform, so each block has the same value. There are only 2 entities, an honest stakers and an adversarial staker with alpha stake. That's also a good question for follow-up work, like how does the situation change if we assume more than 2 adversarial parties? Yeah, one more important simplifying assumption is that stake ratios do not change throughout the course of the attack. That's also pretty natural. We assume synchrony. And in the strategy space, we assume honest behavior when we don't do selfish mixing, and also we don't do forking. Then we assume selfish mixing and ex ante reorgs or forking. So these are the 3 things that the adversary can do. And I also assume here that the adversary do not DOS other validators or other nasty things. So there was a recent paper showing that, maybe we can also reference this in the show notes, by Leo Baheimbach, Jan von Lanten, Luciana Kiffer, Roger Wattenhofer, so some great researchers from ETH Zurich. They showed that in the Ethereum beacon chain, they were able to link IP addresses so they were able to de-anonymize Ethereum validators on the peer-to-peer level. So it's really bad because if I know who is going to be the validators before or after me, and I know their IP addresses, which is really easy according to these researchers to get this information, then I could just selectively DDoS these guys, and maybe I could even increase more my manipulative power on the RANDAO. But let's assume that we don't do these nested things, but in reality, the adversary could do much more. Okay, so one other natural question that I always receive from people is that, can we detect random manipulations? So what about selfish mixing? Imagine that there are 4 tail slots and the adversary misses 2 tail slots. So in the beginning, the adversary has 16, 2 to the 4 possibilities, publish, not publish, publish, not publish. But on chain, we only see 4 possibilities because only these 2 slots were published. So more generally, if the adversary has n tail slots and k among these n were missed, then we typically see only 2 to the n minus k scenarios out of 2 to the n. So it's really hard to tell whether these were missed by purpose or they were just missed by chance due to some network latency or some other issues. So the adversary has some plausible deniability, but obviously we could test this with statistical tests, and in fact we do it in the second part of the paper to evaluate, to see whether this miss is happening by chance or not. But for forking manipulations, the situation is simpler because remember, if we fork out the honest guys, then all the RANDAO contributions of all these blocks are publicly visible. So we can recompute the state with or without the honest guy's contribution, and we could see why this forking happened in the first place. So forking is detectable. Selfish mixing is kind of plausibly deniable because we don't see the full state space. Okay, this is the largest part of the paper where we model this as an MDP and solve this MDP. This is where all the technical difficulties lie. This could be just on its own like a 1-hour talk. Yeah, we solve this MDP with standard tools like policy and value iteration. I'm skipping it now for the sake of your and my sanity, but for the paper, for the full papers, hopefully we are going to finish it soon. You will be able to see the full details. So let me just give you the summary of the theoretical results. So x-axis here is the stakes, the proportion of the stake the adversary owns. The blue line is honest behavior. So if you have alpha stake, then on expectation you should get alpha proportion of the blocks or of the slots. If you do selfish mixing, that's the up to that Weinberg paper previously published at AFT24, then you can increase your share. And we see that the red adversary uses also forking strategies, and that also already gives you an advantage, but this difference is only articulated when for larger entities. And the green line is the number of forked out blocks. So the point here is that if such an adversary does this on a systematic level, then also the chain quality will decrease quite a bit. So that could be also an indication that such a manipulation happens. Oh, and the last line is, since the adversary in some slots needs to miss a few blocks, this is the total number of slots that the adversary controls. So it's even larger than the number of blocks that the adversary proposes. I also remember that mentioned this target slot utility. So your sole purpose is just to get slot 16 or 17 or whatever, and because it has an NFT mint or NFT launch or airdrop, and you want to get all the juicy MEV block. So in this case, you can manipulate the RANDAO even more, which is not that surprising. So let's say Lido would have like almost 50% of chance to get a specific slot in the next epoch. Okay. this is maybe one of the most interesting figures of this work, is that, so we solve this Markov decision process, we look at the stationary distribution, and we record which strategic behavior we see by the adversary. And ideally, this figure would be fully blue. So that's what we want, namely that the adversary or everybody acts honestly because there's no bias in the protocol. But sadly, the protocol is biasable. This distributed randomness beacon is biasable. And we see that forking gets really important after this 15, 20% threshold. And then selfish mixing gets less and less articulated. It gets less and less important, and forking takes over. So forking seems to be a more powerful way to manipulate the RANDAO. Regret is a type of forking. If you remember here, if you go back to the decision tree, here after seeing the honest guy's RANDAO contribution, the adversary can reconsider its choice and decide, okay, I give up, I forego my forking plans, and instead I will just build upon this guy's block. So this red dotted box, this we can consider it, basically it's a type of forking or selfish mixing. So we just call it regret or reconsider because it's hard to characterize it either forking or selfish mixing. So we just call it as regret. Okay, so this was the theoretical part. And yeah, if you look at these two lines, the brown and the red, these are the numbers here. So we can slightly improve the numbers of Alpturer and Weinberg, especially for larger entities or for the coalition of staking entities acting as one entity. They could, so for instance, if you have 30% of the stake, you can get almost 33% of the stake. Yeah, and we can discuss whether it's alarming or not, whether these numbers are too much or not. Yeah, I will leave it up to the discussion at the end of the talk. Okay, so let's jump. If there's no question, or feel free to interrupt me anytime. If there's no question, let's wrap up the theoretical part and let's go to the experimental part of the work. Maybe I will just wait for a few seconds, or if there's any question in the chat, I don't know.
I've got a quick question. In terms of how these effects like compound, right? If you have 20% stake, but then you're ending up with, or I guess 30% stake, but then you end up with 33% of the slots. That kind of can keep compounding for giving even more power in the selfish mixing context. But does that affect forking? Or is like the set of stake for the attesters just kind of constant so that these things don't compound over time to even get you more and more power?
Yeah, so the thing is that in the MDP, we assume that the stake of the adversary is constant, but obviously what you can do is you could take all your profits and create more validators and increase your share, but we don't model this compounding effect of an ongoing attack. But it's a good point that if the attack is ongoing and you reinvest your profit, then essentially your relative share of the stake increases. So, but we don't really model like how many rounds it needs to take over. I guess that's your point, right? That if you keep doing,
I think really like if in my current epoch I have 20 slots and I use that to leverage that in epoch +2, now I have 22 slots. I'm going to have even more powerful selfish mixing characteristics or probability, right? But I guess so yeah, even without reinvesting for a larger stake, just by the fact that you then have more control over RANDAO via control of those slots. Yeah.
So without reinvesting, these numbers refer to the number of slots that you have at infinity. So without reinvesting, these are the numbers. these are the so these numbers mean that if I have alpha stake, I will have it's the number of slots will converge to these guys.
Okay.
Obviously, what you could do in practice is that given all this profit, you can reinvest it, but we do not model it in the MDP. So that's also a interesting question, but it would make the MDP even more difficult. I don't even want to think about it because forks and handling forks nicely and write it up, it's already a huge pain in the ass. But it's definitely interesting what you're saying. But yeah, it would
If I
just
can ask
make.
one other quick question.
Please do.
You showed
Please do.
the strings for the ex ante forking. Is there any stake amount that you can hit to where you have two honest blocks that you can fork out, or does the weight become too heavy at that point?
Yes. So we have this lemma. Oh wait, where is it? So if you want to, yeah, you can definitely do. So if there's a string like this, in your case, like h equals 2, I don't know, pick your favorite A1. And so note that this adversarial slot does not help. So if it wouldn't help if there was more A's here, so that's why we only need to parameterize this string by A1 and H. So if you plug into H and A1, you will get some alpha. So the TLDR is that you can definitely fork out more than one blocks, but then alpha gets trickier. These were just running examples just to simplify it and give some intuition. But if you have, yeah, you can definitely fork out more than one blocks.
Cool.
And this is the formula, and this is a simple lemma, and you will find it in the paper, hopefully very soon out on archive.
Cool. Appreciate it.
Thanks for the question.
I have another question. Like, it seems like the advantage of the adversary kicks in only after like it has really significant share of the stake, like
True.
past 25%. And like even in this like a very high mm, stake regime for the adversary, like it gets roughly at maximum like 10% advantage. So my question is like if like how should I interpret this? Should I interpret this as okay, this is just the attacks we know, and there could be other like ways to manipulate RANDAO and that are way more effective than this? And should I take this as a signal that we need a like provably non-biasable RANDAO, or is this really like we kind of believe that this is the best attack we can do, and then I just need to adjust my security parameters by like this advantage? Like if previously I was okay with somebody holding, I don't know, 33% of the stake, now I'm okay if they keep like, I don't know, 23% of the stake. How do you feel about this? Like, is it the first one? Like, this is just a signal and there could be better attacks, or the second one that we need to adjust our parameters and this is the best attack?
So Daniel, if I remember, had this great point that we should. So I think okay. So two things. I think the strategy space could be only increased if we either consider ex post reorgs. One, two is there's this. You can manipulate the sync committee, so you can manipulate slightly the number of attestators that you control in an epoch in a slot. We don't model this, but I didn't give much thought about manipulating the sync committees. I don't think it will give much edge, but these are famous last words. We don't claim optimality, so it really depends on the model. So I think these are not final numbers. If you refine the model and you are willing to bite the bullet and solve an even more difficult MDP, then and relax these assumptions I told here. So for instance, you assume that the adversary can DDoS certain validators, or you assume that probabilistically there could be these ex post reorgs happening, or you even want to model, as Daniel pointed out, this compounding effect so that you reinvest the profit that you got, then obviously you could claim even more numbers here. But then it gets really technical, and it honestly it is already really technical to model forking and ex ante reorgs. So and if you want, you can even factor into MEV. Then it's a lot of complexities already. So yeah, we already mentioned like 4 things for future work. MEV, modeling MEV, so slots are not uniform, modeling probabilistically ex post reorgs, modeling compounding, the possible manipulation of sync committees, so the adversary could somehow try to increase the number of voters in a slot. So these are already 4 strategies that we don't consider. So I think the adversary, if it really wants, it could even claim more slots, more blocks than we have here. Yeah. I mean, my point is that ideally this figure should be blue. So this is already really bad. Even so, you see that selfish mixing is dominant so everywhere, even for a home staker. If you have a tail slot, and yeah. Okay, let's jump into the theoretical part. Sorry, experimental part. So this is so let's find out whether all this that we were talking about happens at the time of recording. So what you can see in this figure is that x-axis is the different major staking entities, and the y-axis is the length of the tail slot. So the way you need to read this figure is that, for instance, how many times Lido had a 4-length tail slot, and the answer is 692. And among these 692 epochs, when Lido had a 4-length tail slot, Lido missed at least one tail slot 3 times. So in 3 different epochs, Lido was missing at least one tail slot. And we could test this with statistical tests, whether these numbers are a lot or no. So, I mean, if somebody would be really strategic, then here the misses would be much higher. What we also look into in the paper is try to see how much money. So it seems just by looking at this figure, without mentioning any statistical tests, it seems that there's no ongoing systematic exploitation or of the RANDAO, at least using selfish mixing. And so what we see here, again, the blue line is the honest. That would be that's the actual number of slots that Lido gained. But if Lido would have used selfish mixing and even forking, then Lido could have claimed like 200,000 slots more, or like 100,000 slots more. It's hard to convert this number of slots into actual USD cost, because it's hard to really map the value of each slot. So we just report how much more slots could have proposed Lido. So what we looked into is we checked the number of slots that. So we look at only the epochs where all the tail slots were proposed by each entity, and we record how many slots the RANDAO gave to the entity. So this would follow a sum of binomial distributions. Note that the parameter of the binomial distribution is 32, and some alpha, where alpha is the stake of the entity, but this stake changes over time. So essentially the red line, what you see here, is a sum of binomial distributions with different alpha of the given entity. And the blue bars is the actual distribution that we observe. And then we can test this with chi-square test or Kolmogorov-Smirnov test or some statistical closeness test, whether the blue bar, whether the experimental distribution comes from the predicted theoretical distribution. And in fact, what we find is that we cannot reject the null hypothesis. So most likely, so meaning that at least statistically significantly, there is no difference between the experimental and the theoretical distributions. But still, this does not exclude the possibility that they sometimes miss on purpose. But at least on the grand scheme of things, we don't see much changes. Okay. What we see here is at each possibility. So if they have a lot of slots, they could choose from many scenarios. And what we see is oftentimes these entities choose a scenario which is worse. So meaning that they could have done better. And in fact, in the paper, we compute for all these epochs, if they would have chosen the best possible scenario, then how many more slots they could have gained. So the point here is that they not always choose the best possible outcome of the RANDAO, perhaps signifying that there's no ongoing RANDAO manipulation. Okay, again, this is just, we try to, maybe I'm going to skip this. Interestingly, there was only one example of ex-ante reorg. So far, there was not any ex-ante reorgs happening in practice, only one, which is not that interesting. There was many ex-post reorgs that we found. If the preceding block has less than 40% of the votes, then as discussed before, 40% is the proposer boost, then we can fork out the preceding block. Maybe the validator is incentivized to fork out because of MEV. So this block has, the validator sees that the preceding block has little votes and a lot of MEV, then I want to capture all that MEV in my own block, in my own slot. Or the adversary could be incentivized to do this ex-post reorg because it would give an advantage in the RANDAO outcome. And we were trying to see whether these are correlated or no. So if an entity would manipulate the RANDAO, they would only optimize for the RANDAO if the MEV is low. If the MEV content of the preceding block is low, then I'm incentivized to optimize my behavior, my strategic behavior for optimizing the RANDAO outcome. But they seem uncorrelated. So the x-axis is the RANDAO outcome normalized. Y-axis is the MEV of the preceding block in VE, the smallest denomination of Ether, the currency of Ethereum, and we show it in the paper that they seem to uncorrelated. So most likely, currently, people just focus on MEV, but maybe in the future this will change, and they will try to incorporate the RANDAO content of a block into MEV, or they will look at both of these things. Okay, so here maybe we can slowly wrap up. I will just want to give you some food for thought or just philosophical questions that we started with prior to the recording. Yeah, maybe like, why don't we see RANDAO manipulations yet, even though they are highly incentivized to do so, to get more slots? So it seems that currently validators are economically act irrationally. Are we happy with this level of manipulability? That's the main question. Or we just accept that we are using a biasable distributed randomness protocol. Should we fix the protocol? shall we just rely on social consensus as a fix? I mean, that sounds like traditional finance again. Shall we replace the RANDAO? When shall we replace it? My opinion is that we should strive for cryptographic guarantees for unbiasability, and there are many tools to achieve it, like verifiable delay functions, weighted threshold VRFs. Yeah, and we already discussed future work, modeling the RANDAO manipulations with MEV in mind. The block value is not uniform. Are there any more strategies that we didn't cover so far? There's a nice upcoming work talking about RANDAO bribery markets, and two researchers from the EF, Ethereum Foundation, Arantxa and Gottfried, are analyzing the possibility of such market. So imagine you are a home staker and you have a few tail slots, then you can sell the right. So you could publish before your RANDAO contribution, and you could say that if you pay me enough, bribe me, and if you pay me enough, then I will withhold my block. I'm going to withhold my block in that case. So you can essentially auction off the right whether to publish or not publish a block. And in fact, you can even do this trustlessly, implementing this logic in a smart contract. Yeah, I think one of the major future works is to fix the RANDAO. One quick fix and easy fix is that if we make the epochs longer, then the manipulation gets less and less. Smaller proposer boost would also help decrease the possibility of forking for ex ante reorg. VDFs, single secret leader election, and other cryptographic protocols as VRFs, or other cryptographic primitive might be interesting. Yeah, if you're interested, I mean, I think we can open up now the floor. If you have any thoughts about it or any feedback, comments, critique, I would love to hear it. And thanks a lot for Mohammad for inviting me. And yeah, we can, if you want, we can talk about all these questions. Thanks a lot for your time. And yeah, I think we can open up the floor.
Thanks a lot, István. Very nice presentation. I don't see any questions in the chat, but I mean, my feeling is like this is a great work, especially like it tries to push forward like what is our understanding of like the advantage of like an adversary in this scenario. But like I'm really kind of worried about all these things because like in the last part when you mentioned like there could be a market for this, it
Yeah.
kind of feels like we could use this Ethereum, this beautiful coordination tool to fight Ethereum.
Yes.
Like
And
but
like you don't need any fancy cryptography to implement this bribery market. Essentially, you just want the possibility to verify BLS signatures. So and
right.
there will be an upcoming fork, Pectra, where we are going to have precompiles to essentially verify BLS signatures in smart contracts. So such a smart contract, I think, like if we just sit down here for half an hour more, we could easily implement it. Yeah, so such a bribery market is really non-trivial to build, but it's kind of straightforward to do so.
We have a question by Yulan. Go ahead, Yulan.
Yeah, I just wanted to comment on the philosophical questions, I guess. So you mentioned VDFs, so verifiable delay functions, and the Ethereum Foundation has been doing a lot of work since 2017 on VDFs. They failed once to launch using Velorovsky VDF, and then they kind of moved on to try with the Minroot based VDFs, and they've actually, yeah, here they are. So I got a min-root based ASIC VDF here. That was the result of the collaboration between Ethereum Foundation and Protocol Labs and supranational, super cool devices, which sadly got broken theoretically last year. So they're not completely broken. I mean, but Ethereum Foundation has decided to move on and kind of forget about them. So it's really sad, I guess, on that front. But yeah, I'd be very interested in seeing what we could do with, like, what's the next steps with min-root VDFs, because the attack that was discovered, I think, was somewhat unpractical, requiring something like 2 to the 25 processor and 2 to the 40 memory and stuff like that. So, but yeah, I'm not sure. From what I've understood, talking to the EF people, it seems VDFs are maybe not the priority anymore to replace RANDAO, even though they had been from 2017 till like 2023. Yeah.
I mean, there are also other possibilities to instantiate the VDF using repeated squaring in a group of unknown orders. So that's also a possibility. Min-root is not the only option. Although, yeah, sure, there are many challenges down the road, even if we choose RSA or class groups. But I think there are other cryptographic tools we could use, like weighted threshold VRFs, which is a cool recent work by Surav Das, Alin Tomescu, and others. So I think that's also something the community could look into. So there are other ways to instantiate an unbiasable distributed randomness beacon. VDFs is not the only one. Yeah, but obviously we need to find together the consensus on what to work
Yeah,
on.
no, I agree. I just wanted to kind of try and answer some of these questions, because you were asking, like, should we fix RANDAO? And I think everybody agrees we should. And Ethereum Foundation has invested millions in working on BDF devices to try and replace it before the theoretical tax was found, which is a bit sad. But yeah, so I think the consensus, everybody agree we should fix it. The question is, yeah, how? And yeah, I agree. I mean, threshold variable random functions are something I'm convinced do work, but I might be a bit biased.
I would be the happiest person alive to see time-based cryptography in practice and deployed. Would be super nice.
Yeah, I mean, it has been so many applications, like we could practically solve MEV as well.
Yeah. Maybe it's never going to happen. I don't know. But yeah.
Great. I think we can conclude here. Thanks a lot, István, for the presentation. It was great.
Thanks a
I
lot.
think thanks everyone for joining. Take care. Bye bye.
Yeah, thanks a lot. Bye bye.
Thank you. Bye bye.